Imagine you're holding a perfectly ordinary loop of string, nothing fancy, just a little circle of thread, ends tied together. Now you make a knot in it, a good one. Tug it tight. There it is, a knot. Solid. Real. Annoying even. Here's the strange part: whether that knot can ever be untied without cutting the string depends entirely on how many dimensions you're allowed to wiggle it in. That sounds like a cheap magic trick, right? Like I'm about to pull a rabbit out of a mathematical hat. But stay with me, because this is where things start to get deliciously weird. In our everyday world, the one with forward, back, left, right, up, down, once you tie a knot in a loop, that's it. You can twist it, pull it, stretch it, but unless you cut it, that knot is there forever. It's a topological fact of life. Sailors know it, shoelaces know it, your headphone cables know it better than anyone. But suppose, just suppose, there were one more direction you could move the string in. Not just the three we know, but a fourth direction at right angles to all the others. In that world, you could take that same knotted loop and slide part of it around the knot in a way that's absolutely impossible here. The knot would just come undone. No cutting, no cheating. It would be as if the knot had never existed at all. So here's the paradox: is the knot a real, physical thing, or is it just a consequence of being trapped in too few dimensions? That's the kind of question that makes your brain sit up a little straighter. We're used to thinking of dimensions as just directions you can point: length, width, height. Very respectable. Very well behaved. But dimensions are sneakier than that. They don't just tell you where things can go, they decide what things are even possible. Let me give you a simpler example. Take a straight line drawn on a piece of paper. That's a one-dimensional world. Really, if you're a little creature forced to live only on that line, you can move forward or backward, and that's your whole life story. Now put two of those little line creatures on the line, with one standing between the other and a delicious crumb of food. The hungry one wants to get past. But in one dimension, there's no around, no step aside, no let me squeeze by. The only way past is through, and if they're not allowed to pass through each other, they're stuck forever in a tiny traffic jam of destiny. But we smug two-dimensional giants look at that and laugh. Just step off the line, we say. Go around, except they can't. Around doesn't exist for them. It's not that it's hard. It's not that they're clumsy. The very concept is missing from their universe. So already, with just one extra dimension, impossibilities melt into trivialities. Now move up one step. Take a flat world, a sheet of paper again, but this time imagine little flat creatures living on it. They have length and width, but no height. If you draw a circle around one of them, you've built a prison with no walls and no ceiling. From our point of view, it's nothing, just a loop of ink. But for them, it's an inescapable barrier. They can run all they like, but every path leads back to the line, unless, of course, you cheat. You, the three-dimensional being, just pick them up off the page and plop them down outside the circle. To them, you've performed a miracle, a teleportation, a violation of the deepest laws of their physics. To you, it's barely worth mentioning. And that's the unsettling idea. What looks like an absolute rule inside a world can be a trivial convenience from outside it. So when we talk about dimensions, we're not just stacking up directions like books on a shelf. We're talking about the difference between impossible forever and hold on, let me just reach around. Now let's come back to that knot. In two dimensions, you can't even make a real knot in the first place. Try tying your shoelaces on a sheet of paper without ever lifting them off. Every loop you try to make has to cross over something, and crossing over means one part has to go above or below another, but above and below don't exist on the page. So in a truly flat world, knots are impossible. Not hard, impossible. In three dimensions, suddenly knots are everywhere. They're stable. They have types. Mathematicians classify them the way botanists classify plants. Some are simple, some are tangled monstrosities, and once they're tied, they're genuinely different from a plain loop. You can't smoothly deform one into the other without cutting. But in four dimensions, every knot in a loop of string can be undone. Every single one. The extra wiggle room lets the string slip past itself without ever crossing in the forbidden sense. What was a permanent topological feature in three dimensions becomes a temporary inconvenience in four. So what changed? The string didn't. The knot didn't. Only the number of directions available did. That should make you a little suspicious of reality, because we tend to think that the things we can't do are deeply meaningful. You can't walk through walls must be a fundamental truth. You can't untie a knot without cutting must be a property of matter. But over and over again in physics and mathematics, we find that many laws are really just the geometry of the stage we happen to be acting on. It's like discovering that the reason you can't win a board game isn't because you're bad at it, it's because you're only allowed to move the pieces left and right while everyone else can move them in and out of the board too. Now here's the really mind-bending part. We are those flat creatures, just one level up. We're absolutely convinced that 3 dimensions are the whole story, because that's all our senses report. But history has a way of humiliating that kind of certainty. There was a time when up and down seemed fundamentally different from north and south. Apples fall down, they don't fall north. Clearly, down was special. Then along came a deeper understanding, and down turned out to be just the direction toward the center of the earth, a local accident, not a cosmic rule. So when we say, of course there are only 3 dimensions of space, we might be like a flat creature saying, of course there's no such thing as up. Don't be ridiculous. And if there are more dimensions curled up, hidden, or just inaccessible to our clumsy 3-dimensional bodies, then some of the things we think are permanent features of reality might be more like knots in a higher dimensional shoelace, tight from our point of view, laughably loose from another. That's where the story starts to get really interesting, because once you take dimensions seriously, not as abstract math, but as the architecture of possibility itself, you begin to see that space isn't just where things are. It's what things can be. And that raises a question that's too tempting not to chase. If changing the number of dimensions can turn impossibility into ease, what else about our world is just a side effect of the dimensional cage we don't even realize we're in? Want me to keep going? All right, let's play a game of imagination, the kind that doesn't require any math, just a willingness to feel a little confused for a while. Picture a tiny civilization living on the surface of a huge, perfectly smooth balloon. Not inside, just on the rubber skin itself. To them, that surface is the entire universe. They can walk forward and backward, left and right, but up is meaningless. If one of them tried to explain up, the others would say, up where? You mean north? And he'd say, no, not north, off the surface. And they'd gently suggest he take a vacation. Now here's something fun. If those little balloon creatures start marching in what they think is a perfectly straight line, never turning, they eventually end up back where they started. That would drive them nuts, because in their minds, straight lines are supposed to go on forever without looping back. If you walk straight on an infinite flat plane, you never return home unless you turn around. But on a sphere, the straightest possible paths, what we'd call great circles or loops, you can walk straight all the way around the planet. So one day, a clever balloon scientist notices this. She sends explorers off in different straight directions and carefully records where they end up. After a lot of data and a few lost expeditions, she reaches a wild conclusion. Our world is curved. Everyone laughs. Curved into what? They ask. There is no into. There's only the surface. And she says, I don't know into what. But the geometry doesn't behave like a flat place. Triangles have too much angle. Parallel lines meet. Straight paths come back. Something about space itself is bent. Notice what she's done. Without ever leaving the surface, without ever pointing to an outside direction, she's deduced the existence of curvature, a property that, from our perspective, comes from the balloon being embedded in a higher dimension. But here's the punchline. She doesn't actually need that higher dimension to describe her world. She can do all the physics entirely on the surface. The upward direction is a helpful picture for us, but for her it's just bookkeeping. The curvature is real to her, even if up is not part of her physical space. That's a big shift in thinking. It means extra dimensions can be a useful way of visualizing things without necessarily being places you can travel. Now let's drag this back to our situation. We say space has 3 dimensions. Fine. But when physicists study gravity carefully, I mean really carefully, they discover that gravity isn't quite a force in the usual sense. It behaves more like the curvature of space and time themselves. Massive objects don't just pull on things, they reshape the geometry around them. It's as if we're those balloon creatures again, noticing that straight paths bend near heavy objects. Light from distant stars curves around the sun. Clocks tick at different rates depending on how deep they are in a gravitational field. Rulers shrink and stretch. Space and time stop being rigid stage props and start acting like soft rubber. Now, you can describe all of that without ever saying, we are embedded in a higher dimension. The equations work perfectly well, just talking about curvature intrinsically, the way our balloon scientists did. But the moment you allow yourself the mental picture of a curved surface bending into a higher space, something clicks. You can feel what curvature means. That's the secret power of extra dimensions in physics. Sometimes they're not places you pack a suitcase to visit. They're ways of making sense of patterns that would otherwise look like magic. Let me give you a smaller, more down-to-earth example. Take temperature. Walk around the room and measure the temperature at every point. You can think of temperature as a number attached to each location in space. But there's another way to picture it. Imagine a new temperature direction sticking out of every point. Where it's hotter, the arrow is longer. Where it's colder, shorter. Suddenly the room becomes a kind of bumpy landscape in a higher dimensional space where height represents temperature. No one thinks you can actually climb in the temperature direction. But mathematically, treating it like an extra dimension can make certain problems easier to see. Hills and valleys become gradients and flows. Physics is full of tricks like that, adding dimensions not because nature hands them to you directly, but because they reveal hidden simplicity. But then comes the uncomfortable twist. Sometimes the extra dimensions stop being just a trick and start looking suspiciously real. In the early 20th century, some physicists noticed a curious thing. If you take Einstein's equations for gravity, which describe how space and time curve, and you rewrite them in a space with one extra spatial dimension, something remarkable happens. Part of the geometry in that higher dimensional space behaves exactly like electromagnetism when viewed from our usual three-dimensional perspective. It's like discovering that gravity and electricity are just different wrinkles in a slightly bigger geometric fabric. Now that's either a wild coincidence or a hint that the universe has more structure than we directly see. Here's an analogy. Suppose you're listening to an orchestra, but you can only hear the string section. Violins, violas, cellos, that's your whole musical universe. You notice patterns, harmonies, tensions. Then someone shows you the full score and you realize those string parts are just one slice of a much richer composition involving winds, brass, percussion, all coordinated in a higher dimensional musical space. From your limited perspective, the strings had mysterious relationships. From the full perspective, they're just projections of a bigger arrangement. That word, projection, is important. A three-dimensional shadow on the wall can be the projection of a four-dimensional object passing by. The shadow might twist, split, merge in ways that seem impossible for any ordinary 3D object. But from the higher dimensional view, it's just a simple shape moving around. So here's a delicious possibility. Some of the weirdness we see in physics might be shadows of simpler processes happening in more dimensions than we're aware of. Particles that look distinct to us might be the same thing vibrating in different directions we can't perceive. Forces that seem unrelated might be geometry in disguise. What we call charge or spin might be the way an object is oriented in hidden dimensions, the way a coin can show heads or tails depending on how it's tilted. Except the tilting happens in directions we can't point to. Now, before we run off the rails, we have to be honest. Just because extra dimensions are a neat idea doesn't mean they're physically real. Nature isn't obligated to be aesthetically pleasing to theoretical physicists. But the fact that adding dimensions can unify things that otherwise look unrelated is a clue we can't ignore. It's like solving a puzzle and finding that all the messy pieces suddenly snap into place when you look at the picture from one step back. And here's the psychological trap. We think of dimensions as big, obvious directions like left and right, but nothing says an extra dimension has to be large. It could be curled up so tiny that moving a noticeable distance in that direction requires an absurd amount of energy. Imagine an ant walking on a garden hose. From far away, the hose looks like a one-dimensional line. The ant can move forward and backward along it. But up close, there's another direction around the circumference. The ant can loop around the hose, but to a distant observer who can't see that tiny circular direction, the ant's motion looks confined to a line. What if at every point in space, there are extra directions curled up into microscopic loops? We don't notice them because we're too big and clumsy. But tiny particles might feel those directions, and their motion in those hidden loops could show up to us as properties like mass or charge. Suddenly, dimensions aren't just where you can travel. They're part of what things are. And this is where your everyday intuition really starts to creak. Because we've been treating dimensions like empty stage directions, go left, go right. But in modern physics, dimensions can be bound up with the identity of particles, the strengths of forces, even the number of types of vibrations the universe allows. It's less like adding a new hallway to a house, and more like discovering the house is built out of directions the way a melody is built out of notes. Now, if that's true, if the dimensionality of space is tied to the very menu of possible phenomena, then asking why three dimensions isn't a silly philosophical question. It's like asking why the periodic table has the structure it does. Change the dimensions, and you don't just change how things move. You change what kinds of stable structures can exist at all. Atoms, planets, stars, they might depend delicately on space being just the way it is. So the number of dimensions isn't just geometry. It might be destiny. And that leads us straight into the deeper water, where we stop playing with analogies and start asking what the equations themselves are trying to tell us about why reality picked the dimensionality it did, and what would break or become possible if it had chosen differently. All right, now we're going to get our hands a little dirty, not with heavy math, don't worry, but with the logic underneath why dimensions matter so much to how the universe holds itself together. Let's start with something simple: orbits. Planets going around stars. Electrons buzzing around atomic nuclei. Things circling other things because there's an attractive force pulling inward in motion trying to carry them forward. That balance between falling in and flying off is one of the great architectural tricks of the cosmos. It's the reason you're not drifting through space as a cloud of loose particles. Now here's the twist. That balance depends very delicately on the number of dimensions space has. In our three-dimensional world, gravity and electricity both follow what's called an inverse square law. Double the distance, and the force becomes 1/4 as strong. That square isn't an accident, it comes from geometry. Imagine a light bulb shining in all directions. The light spreads out over the surface of a sphere. The area of that sphere grows like the square of the radius. So as you move away, the same amount of stuff is spread thinner and thinner, following that square rule. But if space had 4 dimensions, the surface over which things spread would grow like the cube of the distance. In 2 dimensions, it would grow only linearly, and that changes the way forces fade with distance. Here's why that matters. For stable orbits, the kind where something can go around and around without spiraling in or drifting away, the force has to weaken with distance in just the right way. Too fast, and things barely feel each other unless they're practically touching. Too slow, and everything crashes together or flies apart with the slightest nudge. In 3 dimensions, the inverse square law is right in the sweet spot. You can have closed, stable orbits. Planets trace out ellipses. Atoms have well-behaved energy levels. Structures can sit in a kind of dynamic balance. But change the number of dimensions, and that balance goes haywire. In a universe with more than 3 spatial dimensions, gravity would drop off faster than inverse square. Orbits would be unstable. A small disturbance in a planet would either spiral into its star or drift off into deep space, never to return. Atoms as we know them wouldn't hold together in tidy, predictable ways. Matter might still exist in some form, but not the rich, layered, long-lived structures we rely on. In fewer than 3 dimensions, things get weird in the other direction. In 2 spatial dimensions, for example, the force laws change so much that the familiar picture of atoms and inverse, square binding just doesn't work the same way. The whole idea of inside and outside an orbit becomes slippery. So the fact that we have stable solar systems and stable atoms might be telling us something profound. 3 dimensions aren't just a random choice. They might be the minimum needed for complexity that lasts. That's already a little spooky. It suggests that the dimensionality of space is tied to the possibility of chemistry, biology, and nosy creatures who sit around wondering about dimensionality. Now let's make it even stranger. Forces in modern physics aren't just pushes and pulls. They're tied to symmetries, deep rules about what can change without changing the underlying physics. For example, you can shift the electric potential by a constant amount everywhere and nothing observable happens. That symmetry isn't just a mathematical curiosity. It demands the existence of the electromagnetic field. And here's the punchline: the kinds of symmetries you can have depend on the number of dimensions. It's like musical harmony. In 1 dimension, your options are limited, just a line of notes. In 2 dimensions, you can start forming chords on a sheet. In higher dimensions, entirely new harmonic structures become possible. The space in which your physical fields live determines the patterns they're allowed to form. When physicists try to unify the known forces, gravity, electromagnetism, the nuclear forces, they often find that the mathematics behaves much more elegantly in higher dimensional spaces. Equations that look messy and unrelated in 4-dimensional spacetime start to look like different faces of the same object when you add extra dimensions. It's like looking at the shadow of a machine on the wall. From one angle, you see a circle. From another, a rectangle. They seem unrelated until you step back and see the 3D object casting both shadows. So maybe the different forces we see are just shadows of geometry in a space with more dimensions than we experience directly. But if that's true, why don't we notice these extra directions? Why can't we just step sideways into the fifth dimension the way we step onto a chair? This is where that garden hose idea becomes more than a cute picture. Imagine again the ant on the hose. From far away, you only see one dimension along the length, but up close, there's a tiny circular direction wrapped around. Now suppose that circular direction is incredibly small, not millimeters, not atoms, but trillions of times smaller than a proton. To move noticeably in that direction would require energies far beyond anything we can produce. So as far as everyday life is concerned, that direction might as well not exist. You and I are like enormous, blurry creatures who can only move along the long direction of the hose. The tiny curled up direction is there, but it's hidden in plain sight. Some modern theories suggest that extra spatial dimensions, if they exist, are compactified like that, rolled up into microscopic shapes at every point in space. And the exact shape of those curled up dimensions could determine the properties of particles, the strengths of forces, even the number of particle types that can exist. In that picture, space isn't just three big directions plus some tiny ones. It's a fantastically intricate structure where every point contains a little geometric jewel box of hidden directions, all vibrating in particular ways. Particles then become less like tiny billiard balls and more like notes played on those tiny geometric instruments. Their masses, charges, and spins are like the tones that come from different vibrational patterns in the extra dimensions. So when you ask, what is an electron really? The answer might be a particular mode of vibration that involves motion not only in the big directions we know, but also in some of these tightly curled ones we can't directly perceive. Now here's the part that makes even seasoned physicists sit back and grin like kids who've just taken apart a clock and found a secret compartment. If geometry in higher dimensions can give rise to forces and particles in lower dimensions, then maybe what we call laws of physics are really just statements about the shape of space at its deepest level: charge conservation, geometry; particle types, geometry; interaction strengths, geometry. It's as if the universe is less a collection of things obeying laws and more a single geometric object whose shape dictates everything that can happen within it. That's a radical shift. We're used to thinking of space as the empty stage and physics as the play. But in this view, the stage and the script are the same thing. Change the stage's dimensionality or shape, and you get a different play, different particles, different chemistry, maybe no chemistry at all. And that brings us back to something we touched earlier, but didn't fully appreciate. Dimensions control not just motion, but possibility. In one dimension, you can't tie knots. In two dimensions, you can't build overpasses without intersections. In three dimensions, you get stable orbits and knotted loops. In higher dimensions, knots come undone and force laws shift. Each step up or down rewrites the rule book of what structures can exist. So when we ask whether there are more dimensions, we're not just asking about hidden directions. We're asking whether the apparent complexity of our world might be the projection of a simpler, higher dimensional order, and whether some of the fundamental features of reality are really just artifacts of the dimensional slice we happen to inhabit. And here's the truly humbling part. We don't get to choose the answer based on what feels intuitive. Nature doesn't care what we can picture easily. Our brains evolved to throw spears and gossip, not to visualize 10-dimensional manifolds. So when the equations start whispering about extra dimensions, we have to listen, even if our intuition kicks and screams. But we also have to be cautious. Beautiful mathematics has seduced physicists before. The universe has a say, and it speaks through experiment. So far, extra dimensions remain a possibility, not a confirmed feature. We're like detectives who found a set of footprints that might belong to a suspect we've never seen. The trail is suggestive, not conclusive. Still, even as a possibility, the idea does something profound to your sense of reality. It tells you that what you perceive, length, width, height, might be just the tip of a much richer structure. That the solid, obvious world is a kind of slice through a deeper geometry. And once you start thinking that way, it becomes very hard to look at space as empty ever again. It becomes more like a living fabric, with folds and curls and hidden directions that quietly determine everything from the mass of an electron to the lifespan of a star. Which leaves us with a question that's less about equations and more about perspective. If our entire experienced universe might be just a thin cross-section of a higher dimensional reality, what does that say about our place in it and about the way we should think about time, existence, and the limits of human understanding?